So today I'm going to introduce a new topic. We're going to be getting into the RISC-V microarchitecture, meaning that's the internal design of RISC-V. But I wanted to spend a few minutes to take a look at the always_ff and sequential logic that we covered last time, and do another demo of that. So the first issue here is there is often confusion about the term register. What's a register? And it's a little vague because when I say register, you guys probably, your first thought is probably like a register that's in RISC-V, like a architectural register, meaning that one of the memory locations in the register file that you can address in your program, in your assembly language program, right? But there's also a notion of a register from the circuit perspective, which is essentially just a multi-bit flip-flop, meaning it's a memory element that you can instance in a digital logic circuit. That's also called a register. Basically, a register in that sense is an element that can store one value. And usually registers are edge triggered. So they capture data on either the rising or the falling edge, and the data they capture can have as many bits as you want, but there's only one location in there. So when you clock something in a register, you take all the bits coming in and you store them inside the register. Does that make sense? So there's a lot of confusion because I'm going to be talking about registers a lot, but you should know that I'm not talking about the addressable kind of registers that are in the register file in the assembly program. I'm talking about a multi-bit flip-flop. And so here's how you make one in System Verilog. And I showed this last time towards the end of the end of the lecture rather. So basically, you can build a register in essentially one line of code. Although I have it's 2 lines of code. These 2 lines are what I'm talking about. I have a new line there for readability. But basically always_ff at pause edge clock, and then Q gets D. Right now you can also add additional features, like in this case I have a reset. So it's a synchronous reset because it's resetting Q without waiting for the clock to do it. Right? It's because only the clock is in the sensitivity list. So I have a synchronous reset here, which I can reset this flip-flop with a reset input. And I also have an enable input, which allows me to specify whether I want the flip-flop to be enabled, meaning that it latches on the rising, not latches, it registers input data on the rising edge of the clock, or if it's not enabled, it just holds the data in there, even if you get it rising edge of the clock. You guys with me? Okay, so that's a register, and then of course I declared Q and D up there. So you could see how many bits. This is a 4-bit register. And of course you can, the register size is going to depend on, in this case, 2 things. The size of D and Q, which should be the same in this case, because I'm not, I just say Q gets D, right? So I didn't specify like any bit bounds here. So it's assumed these are the same width. And of course, when I reset it, notice there's a 4 there. So that 4'B0, that's 4 bits of 0. So this is designed to match the declaration of Q and D. So it's a 4-bit register. Okay. Okay. So let me just show an example of that. So I'll open up the. Okay. So if I go up here and hold on, lecture stuff. And I'll create a file called top.sv and module top semicolon no inputs outputs and module. And the first thing I'm going to do is, now I'm going to mix together like test bench code and behavior in one module here. So this will be, obviously this is not synthesizable. So I'm going to have logic clock, and then I'm going to say always begin clock equals 1, 5 units of wait, clock equals 1 apostrophe B 0, 5 units of weight, and end, right? So that'll create a clock. And then I can do always at, always underscore FF at pause edge clock, begin and end. And I'll create some stuff, A, B, and C. Actually, I want to make these 8-bit, 7 down to 0. So A, B, and C are 8-bit wires. And I want to generate a random sequence of values on A. So I'm going to create what's called a linear feedback shift register. So I'm going to set A to be A bit 4 XOR A bit 0, comma, A 7 down to 1. Okay, so what this does is it takes the previous state of A, bits 4 and 0, and it XORs them together. And then it takes the result of that and it shifts it into the left-hand side of A, shifting bits 7 down to 1, to the right. And of course the bit 0 goes away, right? Gets dropped off, right? So this basically just takes two values out of the old A, combines them with an XOR, and then uses that as the shift in bit and does a right shift by one bit, okay? Now in order for this to work, I have to initialize A. So you can do that when you declare it. So I'll just set it up as 8 bits of 10101010, and I'll get my little random sequence of values on A, hopefully, if that works. And then I'm also going to set B to be A and C to be B. So this is going to take the old value of A, put into B, the old value of B, and put it into C. So C will be the value of A delayed by 3 cycles, right? Sorry, 2 cycles. 2 cycles, right? Because I'm going to take A, I'm going to put it into B in the first cycle, and then I'm going to put it into C after the second cycle, okay? Meanwhile, A will be, should get a random number sequence. And of course, the value I initialized it with is the seed of the random number sequence, right? Which is, I think, AA and hex, right? Okay, so then vlog top.sv got an error somewhere. Oh, thank you. Oh yeah, end module. Forgot the O. There we go. Still got an error. Oh, can't open it in read mode. Really? Okay.
Oh, are you not in the right directory?
Oh, you're right. I am. I'm not. Thank you. I need to go to lecture stuff. Yeah, there we go. Thank you. Vlog top.sv. Okay, now we're good. Now I'll say vsim top, and that will pop up the simulator. Now from this point on, if I make any changes to that top file, I'm just going to compile it in the command line, the little, I'll just do it down here. I'll type vlog top.sv, and I can recompile it from the console. I don't have to go back to my terminal. So now the problem is, and I showed you guys this last time, I've got top selected over here on the left-hand side, and what I expect to see is my signals here, over here, but they're not shown because ModelSim is, I don't know why, they just started doing this in this version, in one of the more recent versions. They optimize out the signal. So if you go to, if I go over to Start Simulation and I click Optimization Options, I can say Apply Full Visibility to all modules and hit OK, and then I have to select the top and hit OK. So basically what I did there was even though I started simulating top when I started ModelSim because I said ModelSim space top, I had to just re-simulate it now to have it show me my signals up there. Now, if you're interested how to do that from the get-go, there is if I hit the up arrow in the command line, it's going to show me the command that it used. everything you do in the GUI will have corresponding commands down here. So if I would have typed vsim work.top, and I think the work dot is redundant, I could have said vsim top, I would have had to add the option -v opt args equals plus ac, but I'll never remember that. So that's something I'll just do through the GUI. But like I said, I could have issued this command in the terminal, and I could have avoided that extra step. Okay, so I got it going, and oh, one other thing I want to show you too before I forget. If I go back in there, there's one of the problems, and I showed you this last time too, is that if I run this and then I add my signals here to the wave, the problem is that, and I run it again, the problem is you'll notice that all the data for these signals that was generated before I added them to the wave is not shown, right? Because it doesn't record the state of these signals unless they're in the wave, right? Which is, again, it's an optimization. The assumption there is that if it records the state of all this, if it logs the state of all signals, you'll run at a disk space, right, if you have a big design. But there is a way around that. If you go to your design, there is a command, and this is optional, but this is something I like to do. I think it's convenient. If you add an initial block in here, you can say WLF dump vars 0, top. And so this is going to issue a Verilog function, I forgot the name, what is it, PLI function? VLI? PLI? It's a Verilog function, starts with a $, and it's in the initial block, and it basically just tells ModelSim to save all the variables. Now that function, by the way, is specific to ModelSim. If you're running this in Verilator or Icarus Verilog, then I believe it's just dump vars. You don't have the WLF. There's different variations of this depending on what simulator you're using. This is not a standard ModelSim thing, standard Verilog thing, rather. So I'm going to save that, and let me test that out, make sure I did that right. Hopefully I remembered that command right. So I'm going to say vlog star.sv. Am I in the right directory? I should be, right? Yeah. Vlog star.sv. Syntax here. Maybe initial. Another typo, sorry. Initial. There we go. There we go. And now I will restart this. Just hit the restart button. And let me go to the wave window. I'm going to delete the waves. I just hit the delete key because they were already selected. I'm going to run this a bit, and then I'm going to right click and say add wave after, yep, and there they are. So it worked. So that's just something you can do. You put that one line of code in your top level, just in your top level module, and it'll make it so you can add waves after you run it. Okay, so you can see let me zoom in here a bit. So you can see A is 55, 2A, 15, OA, 05, 82, 41, A0, 50. Looks like a random number sequence. Is it repeating? No. Doesn't look like it. I don't see the period here, at least on this length of time. So
it goes from AA to AA.
Yeah.
That repeats.
Oh, it does have a period, huh? Yeah. 8A, where's A? Oh, 8, you mean A8?
From AA, repeating.
From AA, okay. So AA, AA55, 2A. No, but it's not repeating. Oh, yeah, here we go. AA, you're right over here. Yeah, okay, so it does have a period. So it's not a great, I could have picked better taps on that linear feedback shift register. It has a repetition period of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 12. That's okay. Well, that's good enough for this example, right? It repeats every 12 cycles. Okay, so you've got A as just the random numbers. B is the one cycle delayed version of A, because B is just a registered form of A. So you can see that basically it's just phase shifted by one cycle. Whatever A is will be picked up by B of the next cycle, and likewise C will be picked up 2 cycles later, just like I said. Okay. Now you'll also see here that C is initialized at the beginning. You might say, well, wait a minute, why was B initialized at the beginning? Well, this is something strange that happens. Notice the very first edge was a rising edge. Because that first edge was a rising edge, I was able to get A and B together with just the 1 cycle delay for C. However, if I were to change my code, I don't know why I started out high. That was a bad decision. Because I wanted to show the uninitialized values at the top, at the beginning. So I'm just going to change my clock, and I'll have it start at 0 and then go to 1. So that'll invert the clock, and then I can come back here to model sim. And again, I have to vlog and basically just restart -F and run. And then go back to my wave. And yeah, so you can see now, because the clock now starts at 0, it's going to wait till the first actual rising edge, because the first thing is a falling edge at the very beginning. So you got that rising edge, and that's when B gets set up, and then C gets set up. Now you might say, A, why is A not unknown? Well, remember, I initialized A. A had an initial condition, initial state, which was AA, right? So I would expect A to be good from the beginning of the simulation, but B and C, of course, have unknown initial states. Make sense? Okay, so that's an example of a register. I didn't, explicitly build it as a register, but that's essentially what it is. In fact, it's kind of 2 registers, so I'm capturing B and C, and they're just acting as a delay line, a delay register. Both of which are 8 bits. I don't have an enable, and I don't have a reset, so they're kind of dumb. They always adopt a new value every positive edge of the clock. Okay, and then A, that random sequence A is kind of just like a test bench, like a test stimulus, and of course I've got clock going, which is would prevent this from being synthesized. Okay, so any questions about that? Yes.
So I'm just, I guess, a little not clear about how non-bounded and bounded assignments are. And so I was just wondering if that first A, the A equal, unbounded, whatever, if you were to make that bounded, how would that change how B and C?
Bounded in what sense? You mean in terms of the bits?
Equal sign.
You mean blocking, non-block. Yeah. That's a good question. So. Yeah, so these were I used non-blocking here. And the reason is because I intended for each of these 3 statements to be 3 separate parallel flip-flop or registers, register, flip-flop, whatever. When you say flip-flop, you usually mean 1 bit, and of course these are 8 bits, so technically they're registers. If I had made these blocking, then they would have collapsed into 1, because this value of A will have been updated by the first statement inside the always statement. But in this case, that's not happening. What's happening is I'm setting A in the first line of code, then I get to the second line of code, and there's an A there as an input, but it's that old A. It's not the new A. It's not the A that I just assigned in the previous line, because these assignments don't take effect until after the always finishes. So these are concurrent. These are concurrent assignments, all 3 of these. If I had used a blocking, then the whole thing, A, B, and C would all be. In fact, we can try it.
So
we can easily test that.
If you use 1 blocking, though, would that still cause the same as changing all of them to blocking?
If I used 1 blocking, like on B, for instance, then A and B would be the same, but then C would be delayed. So in fact, we can try that. I'll just leave it like that. So I'll save that, go back up here, use my up arrows to vlog and restart and run, go back to the wave, and it looks like it made them all. Yeah, this is, okay, so yeah, you can see they're all the same now. This is that kind of, I've had this happen before where you get sometimes you get unpredictable behavior when you mix blocking and non-blocking.
Yeah, that's not like Verilog compliant.
Yeah, I've seen this happen before. Usually when I try to get fancy and do this mixing, it usually kind of blows up in my face, and that's what happened here. It's best to avoid. When you have sequential logic, you should use non-blocking.
Yeah.
Now, you might notice that I use blocking. In fact, actually, you know what? Now that you mention it, I think I might know why that happened, actually. This is getting into a little bit more detail than I wanted to, but I think the reason this is happening is because up here with the clock, I used a blocking assignment. I wonder if this will behave differently. Now you might say, well, wait a minute, how would that affect, how would the clock and the always up there affect the always down there? Unclear. That's why they, in the textbook, they say stick to the convention, but I think this might actually fix it because I've seen this happen before. So again, save that, go back up to the Quest to Sim, vlog, restart, run. Oh, sorry, run. Okay, let's go to wave. Nope, made no difference. Okay, so yeah, I don't know. I always just try to stick to the convention.
Yeah, I think mixing blocking and unblocking is UV in Verilog.
So yeah, I'm just going to change this back to non-blocking, and I don't know why I exited that. Okay, so okay, let's move ahead here. Okay, so that was a register. Now, what about a RAM? What's a RAM? How's a register differ from a RAM? A register, as I mentioned, is one location that's being stored. So you get a rising clock edge or negative falling clock edge, depending on how you design it, and it captures one value. Whereas a RAM does the same thing, except it has different addressable entries inside there. So depending on the address, you can address register locations inside the RAM, right? And so in this case, this is a 1024 by 32 RAM, meaning that 1024 is the depth, and so the address would be the log base 2 of 1024. So this would be a 9-bit address, 10-bit address. Log base 2 1024 is 10 bits. So I'd have to give it a 10-bit address, which would allow me to give it an address value from 0 to 1023, and that will allow me to indicate which entry in the RAM array I want to access. And then the 32 bits is the width of each entry. So the way that RAMs are specified is depth by width, right? Which is the same way that mathematicians do it and the way that C and Java do it, right? But like I mentioned, Verilog switches those in the Verilog syntax. But when you see this, again, it's 1024 depth, 32 bits wide. Okay, so, I just mentioned that. Okay, so how do you write a RAM? Now keep in mind too that what I showed before was 3 registers, or actually 2 registers, B and C, that I kind of defined, but not as independent modules or not even as independent always blocks. I just kind of wrote lines inside an always statement and I got 2 registers, right? RAMs are the same way. You can drop a RAM in into your Verilog code wherever you want. It will be declared the same way we declared the test vectors when I talked about test benches last lecture. So you say logic and then you give it the width, the name of the RAM, and then the depth. So even though everyone uses depth then width, in this syntax it's reversed. It's width first, then depth second, right? So you just try to keep that in mind that Verilog syntax reverses that. And then you can define ways to access that RAM through reads and writes. So in this case, I have an always underscore flip-flop, and I say if write enable, then I want to write to the RAM. Well, when you write to the RAM, you have to add you have to have an address for the RAM. So I have an address here that's declared as 13 bits, 12 down to 0. And a 13-bit address will give me an 8K entry, 8 kilo entry, or 8,192 entry, 2 to the 13th power. That's how many entries, that's the depth. That's the number of individually addressable cells in there. And then the width is 32 bits, so the write data is 32. So the address is, again, is 13 bits, the write data is 32 bits, and I want to define the write behavior as writing on the rising edge of the clock if the write enable is asserted. Now with a RAM, you almost always have a write enable, because RAMs, you only want to write when you intend to write. Because RAMs are intended to hold data a little bit longer term than a register would. Registers are usually, there's no enable because you're just trying to carry data from one clock cycle to the next to create a data path. That's what registers do. Whereas a RAM is like for longer term storage. This is what you use for your register file, for instance, on your CPU. Okay. Now what about reading? I talked about write. Well, this is the reading behavior is defined actually above that, where it says assign read data equals mem ADDR. So mem is on the right-hand side, so it's being read. Over here it's on the left-hand side, so it's being written. Notice I use the same mem. So what this is doing is this is actually creating a write port and a read port, because I can do both of these things simultaneously. I can read and write at the same time, because there's an assign statement which is concurrent with this always block. So I have two ports into this memory. And anything I do, reading and writing here, is going to be happening inside that memory, that one RAM, right? Now I could add another line of code in this always and add another write port. Likewise, I can add another read port. In fact, I can add as many read ports and write ports as I want in this code. But there are practical limits. In real hardware, it's usually not feasible to have more than 2 or 3 ports on a RAM. But in Verilog doesn't care. I can create as many ports on this as I want. But then if I try to synthesize it on FPGA, Okay. Okay. So let me go back to my other example, and let's add a RAM. So I'll come to. So all I have to do to add a RAM to this is basically just declare it. So logic 7, I'll make it 8 bits wide. Again, the width comes first, and then the width will be, the depth will be, let's make the depth 16. So this is a 16 depth, 8 width. So this is a 16 by 8 RAM that I've declared, and then I can say always _FF. I'll add my write port at pause edge clock begin. And I'll say, and I actually in this case I won't put an enable. I'll just have it write all the time. So I'll say RAM of. Now what am I going to use as my address? Well, I can use A. I got a random number generator going here. So I'll say A, and I'll say 3 down to 0. So I'll take the 4 least significant bits out of A, and I'll plug that in as my address, just because it should be a 4-bit address because it's a 16 depth RAM, right? And then I will write in the whole value of A in there. And I have a begin and end on that always, even though I technically don't need it because I just have one statement. So this is going to write every cycle into the RAM, and then I'll have an assign out val to be RAM of A 3 down to 0. Okay, now notice that I don't have, the read is not inside the always, so the read is an asynchronous read, which means that this read statement, because it's an assign statement, is combinational. So anytime the address changes, it's going to read immediately, right? Whereas the write is synchronous. Writes are always synchronous on RAMs. I don't know how you'd build a RAM that could asynchronously write. So typically a write is going to look for a clock edge and an enable, or in this case just a clock edge, right? But the read is, in this case, now I could easily move the read behavior inside the always, in which case I'd have a synchronous read, right? In which case if I want to read, I have to wait to the next cycle to actually get the data I want to read, right? Yes?
I'm not understanding why the writing being asynchronous is a problem. I can take it at face value that it is, but I don't know why.
It's not, because your register file in the RISC-V processor it does have an asynchronous read, because in the decode stage, if you remember from 212, when the instruction starts to decode, the instruction is only available at the beginning of the decode cycle, right? And then you're expected at the end of that cycle to have the contents of the registers, right? You're going to pool the registers that instruction needs out of the register file inside of one cycle. Not wait till the next cycle, but you're assuming that there is a zero latency. I'm going to fetch the instruction, and then inside the decode cycle, I'm going to decode it, meaning I'm going to convert it to control lines, but I'm also going to read the registers that it needs, right? And I'm going to do that inside of a cycle, which means that the register file on the Mips and the RISC-V has an asynchronous read. Okay. So it's not a problem. It just doesn't scale very well. If you make a really big RAM, it becomes difficult to do. It creates timing problems if you scale that up. Yeah, that's why register files are only 32 entries deep. For larger RAMs, like for example the instruction RAM in our RISC-V processor, will have a synchronous read, which is why you have a fetch stage. You have a fetch stage means that I need a whole cycle just to read an instruction. Okay. So it's the same way in the Mips processor from 212. The assumption was reading an instruction was synchronous. I needed a whole cycle just to read the instruction. That's why I have a fetch stage. But when you decode, you're getting the registers within one cycle. So that's asynchronous.
Okay. But you had said, I'm sorry, that does help because I also wasn't super clear on the reading. But I was asking about the writing because it sounded like you do need to be synchronous with writing.
Yes, yeah. I've never writing. So writing, I guess it would be possible to create a RAM that would be maybe a level sensitive write, but making it totally asynchronous, I don't know how that would work because the whole point of a RAM is to capture data on an event and hold it, right? If it was asynchronous, it wouldn't do that. It would just basically feed data through like an identity function, right? So it doesn't really make sense to have a write behavior that's asynchronous, right? It has to be synchronous because you want to have input data that you capture on the edge of the clock and you hold it inside the RAM, right? Which is different from reading. When you read, you can just throw a bunch of addresses at it, and every address you give it will result in an instant, the contents of that address popping out the other end. But for writing, you want that to be synchronous. So generally, you're going to have the write behavior inside the always _FF, and the read can either be in there or not, depending on what you want with the RAM.
So the problem is basically that with writing, if I was just driving it, it would dynamically change if the things I was driving it would. Yeah,
it would constantly be updating, right? You don't want that. You want it to update just at one moment in time, to hold the data. Yeah, so let's take a look at, I need to declare that out val thing. So logic 7 down to 0 out val, and then assign out val. Okay, cool. Save that. I have to compile it and restart, and hopefully out val's, yep, there we go, out val. Now check this out. Not only did out val pop up, but my RAM popped up too. Now the problem with the RAM is that even though I put that WLF dump vars thing, it still won't record RAMs unless you have them in the waveform window. You guys with me? So if I don't, I need to right click this RAM and say add to wave, so it keeps track of that contents of the RAM, and I'll do the same thing for out val. So those should be in my wave window now, and I will run. Okay, so now I got a bunch of stuff. Wait, let's scroll back. Okay, so if I click the RAM, now, by the way, I don't think I showed you this yet, but if you drill down into any of these other signals like C, it's just going to show you the individual bits that make up that signal. So if I click C, I'll see all 8 bits, which usually you typically don't need to do that. But if I do that on the RAM, now I see the individual entries of the RAM, right? And you can see that, of course, they start out as uninitialized. In reality, RAM comes up as random. Well, on an ASIC. On an FPGA, RAM will come up as zeros because this RAM will be initialized when you program the FPGA as part of the programming process. But the simulator is going to show a red line means not initialized, right, for these entries until they get written, right? So you can see what you're seeing is that every time one of these red lines changes, you're seeing entries in the RAM get populated over time, right? And they're being populated randomly, of course, well, semi-randomly, pseudo-randomly. So the first register here that gets, or the first RAM entry that gets updated as address 10. Okay, and then the next one is going to be 5, and then I guess 10 gets updated, and then 5, is it going? Oh no, then we get some down here. Yeah. So when you're debugging your CPU, this is how you're going to do it. You're going to put your register file and plot it, and you're going to see the registers being populated as your program runs, because as your assembly language program runs, it's going to be writing registers, and as it runs, you're going to see those registers pop up, and this is the way you'll know when something happens, because typically if you crash your program or something goes wrong, usually you'll see the activity stop in the register file. Okay, so let's look a little bit more closely here. So the first guy that gets updated is number 10. And what happened there was A was AA. So I took the low order 4 bits, which was A or 10. That was the address. So obviously address 10 gets written. And the value that I write is AA. And notice it happens on the rising edge. Right there. Right? Now, what happens to outval though? Outval, remember I'm reading on outval. And outval doesn't get A until the next rising edge. You see that? That's interesting. Then 5 is the next register. And why does that happen? It's because A was 5, 5. So it went from AA to 5, 5. I peel off that second 5. That's my address. So I'm going to go to register 5 is going to get set to 5, 5, which is the contents, right? And then, so you can see how it's writing, right? The next one is 2A. Why does 2A go to 10? Well, because it has an A in it. So A is 10, and the address is just because I picked the low order 4 bits is the address. Okay. Now outval. Let's see. Outval is assigned. I actually did not expect that to happen. So let's check this out. Let's see what happens when I put let's change it and let's put the read port inside the always as well. So I'm going to say outval is going to get RAM of A 3 down to 0. And I'm going to comment out this line, and then I have to move this guy up. So I'm going to delete that, and I'm going to put it there so it appears before I use it. Okay, so now I'm going to switch outval to be a synchronous read. I'll save that. Okay, now I just want to point out, by the way, too, check out outval. So outval in this case got updated to AA. So I wrote AA and I read AA. There is a cycle difference there. But that is yeah, that's what I got there. Now, why did this updated here? Outval is AA, and so that should have been a reflection of the address 2A. Oh, there we go. Yeah, that's what happened. See, there's a weird coincidence. So I have, if you look at the address, remember the address is the second character of the hex, right? So it's 10, 5, 10, right? So I'm reading this asynchronously because I have an assign statement. I haven't recompiled yet when I changed it. So this is still the asynchronous one. And so 5, 5, sorry, not 5, 5. Got to scroll down, outval, right down here. So outval is AA because it's seeing an address of 10, right? But when does the address appear to it? Right at the beginning when that becomes 2A. You guys seeing that? Now you might say, why didn't I see anything on outval before that? Well, because before that the address was 5, right? So basically what happened here is that I wrote AA to register 10 on this rising edge, right? But then at that same rising edge, I changed the address to 5 combinationally. You guys with me? So in other words, there was no time to ever, when I wrote AA, there was no time to ever read it because but on the same rising edge that I would have been updating AA in register 10, I've now changed the address to 5, and because it's asynchronous, now I'm seeing address 5, and therefore my out val is showing me what's in entry 5, which is in X, right? Wish I could fit all this on one screen somehow. Kind of, yeah, here we go. Yeah, not really, because now I don't, wait, let me drag down, here, let me do this. Take out val, I'm going to drag it up so it, there we go. Okay, yeah, that's a little bit better. Okay, so out val is what I'm reading, and you can see that the minute the address changed to A, I got the contents of A immediately, right? I had a flat line before that because that was the asynchronous reading of address 5. Now you might say, well, you're writing to address 5. Yes, but not until the end of that cycle, right? By the time I write to address 5, my read address is already gone, right? So I never had a chance to read from address 5. I wrote to address 5, but I never read from it because I'm already off to the next address. You guys see that? Now I changed it. I changed the code now to make the reads synchronous. So let's see how that affects it. So if I go back to Questa, vlog, restart. You might say, why do you keep restarting? Restart is what actually loads the compiled, like when you type vlog, it compiles the Verilog, but it doesn't load that new compiled code in until you restart. So you have to restart if you want to, you have to vlog and restart if you want to see changes, the changes to your code reflected in the simulation. Okay, so I just reran that, and now things are different. Now, out val is, or at least they should be different, AA. So out val is going to, no, I don't think that's, oh yeah, sorry, I'm looking at the wrong thing. Out val, notice AA is over here. It's been pushed one cycle to the right? So in this case, basically what happened was, in this third cycle, I read and wrote to address 10 in the same cycle. Okay, I wrote to A to address 10, which you can see updated here, right? And I also read from address 10, but the value I read was the old one, AA, right? Right, no, I wrote to address 5 actually, sorry, scratch that. I actually wrote to address 5, and I think I need a better example there. But I got the, so this is the old version, AA is what I wrote to address 10. Let's see, then I wrote, again, I wrote 2A to 10, which gets written here. But then again, I read from 5, so that's a bad example. I'm trying to find a place where, I guess I don't, I guess I don't have an example where I write and then read the same address the next cycle, because it keeps changing here. But anyway, the point is that these, the reads, if I look at out val is a reflection of the address from the previous cycle. I think that's a more concise way to describe it, right? So AA is, so I've got address 10 I read as AA, address 5 I read as 5.5. Address 10 is read as 2A here. Does it make sense? So basically what that means is when you read, you don't see the contents of the read until the next cycle, right? So the other caveat here is that you might say, well, am I reading 5 here? I am reading 5, but I'm not going to see the result of that until the next cycle. I'm actually reading 10 in this cycle, not 5. Does that make sense? Kind of confusing. So let me show you, I think I have a better example in the slide actually. Okay, so in this slide I have a asynchronous versus a synchronous read. So the top, let's see, in this case the address is changing. The address is 4, 5, 6 and stays there. Same thing down here, 4, 5, 6. On the top one, the read data, the data I'm reading, is, let's see, what am I writing, by the way? I'm writing 0, oh yeah, I'm writing dead beef. Okay, so I'm writing dead beef to address 4. Sorry, to address 6. You see that? So there's dead beef, there's 6, and then there's my rising clock edge. And you can see that when I write to it, which is I'm writing dead beef to address 6 on this rising edge, you can see the read data pops dead beef out immediately, right? The minute that it writes, I see the result. Why? Because I hold 6 on the address. This is the thing I couldn't show you in my demo because my address kept changing every cycle. But notice that address 6 stays, right? So address 6, I write dead beef, and then I read it. But when I read it, the read takes effect immediately as soon as the write takes effect, right? Whereas with the synchronous, the difference here is that I write dead beef to 6, but then the read data in the next cycle is still 6. It's the old value of 6. It takes another cycle before I can read dead beef out of there. So in other words, what happened on that rising clock edge, on this rising clock edge, I put a new value into register 6 of dead beef, but I pulled the old value out at the same time. I kind of did a swap. I gave it a new value and I got the old value, right? The new value went in, the old value came out on read data, right? So you might say, well, what is, well, pretty much it just pushed this dead beef one cycle to the right. That's really the effect. But the important thing to understand is that I got the old value of register 6 here before, in the cycle before. Make sense? Okay, so let's look at a more concrete example. This is the register file that you're actually going to use in the project, in the lab. And this is also the same register file that you guys studied in 212. It's the Mips register file. RISC-V uses the same register file as Mips in the sense that it has 3 ports. It allows you to read 2 registers and write 1 register in 1 cycle. So this would be used for if you had a single cycle CPU, obviously you'd need to do that, or even in a pipeline CPU you'd have to do that, except in a pipeline CPU, the register you're writing and the registers you're reading are from different instructions. Whereas if you had a single cycle CPU, it's all from the same instruction. Okay? So the point is that, and if that's unclear, I'll show you a better example of that in a minute. So there's a clock input and a write enable input, and then there is, and write enable, by the way, is going to come from your control unit. And basically your control unit is going to set that, almost every instruction will be high. Almost all instructions write a register. If it's a branch or a jump instruction, it doesn't write a register. It writes just, it changes the program counter. So unless you're doing a branch or a jump, or is there any I think branch and jumps are the only exception. Of course, if you're doing like a store instruction, it wouldn't write a register either, but we're not doing stores, right? So almost all instructions write a register at the end, right? Except for branches and jumps. But anyway, that's going to be set by your control register. And then read address 1 and 2 are 5 bits each, because there's 32 registers, and those come directly from the instruction fields. You guys remember that from 212? So pretty much you fetch the instruction and you grab 2 groups of 5 bits directly from the instruction. Those are your operands, and you read them both. So you feed those into here. And then you have a write address and a write data. Write address also comes from the instruction. Write data generally comes from the ALU. Okay, so that allows you to do 3 ports, 2 reads, 1 write. The reads are asynchronous. Okay? And then read data 1 and read data 2 are the 2 values you're reading. You guys with me? Okay, so what does the code look like? Well, the code, obviously it looks a little bit more complex than what I showed before, because now we have more ports. And by the way, I packaged all this into a module, and we give you this module, by the way. This is something, you don't have to design this on your own. We're going to just give this to you as like an IP block that we're going to give as part of the project skeleton. But basically, it's important for you to understand how it works so you can interface to it. So you're going to have, the actual memory is called mem. I called it RAM in my example. It's called mem. 32, 32. 32 is the width, 32 is the depth. Obviously 32 is written as 31 colon 0, 31 under 0. And then there's two assign statements that take care of the two read ports, asynchronous read ports, so they're asynchronous, so you use assign. Now you might say, what's all this crap here? Well, there's some extra stuff in here. You got a couple extra features for this register file. The first one is, if you read from register 0, you should always get a value of 0 because that's defined in the instruction set register spec. So we have a special case that says, if read address 1 is 0, nah, just give 0. Just spit out 0. Don't read the actual entry 0 in the RAM because that's untouchable. Like, you can write to it. You're allowed to write to register 0, but if you read from register 0, you don't get what you last wrote. You get 0 back, right? Now, likewise, we have this other issue. If you read and write to the same register at the same time, what happens? Well, according to the waveform I just showed you here, we do that, don't we? Yeah. Yeah, we do, because in this case, there's only one address, right? We have a read address and a write address. In this case, there's only one address, and we set it to 6. But regardless, we're still reading and writing to that address at the same time here, right? So in this cycle, from this rising edge clock is the third one down. This rising edge to this rising edge, that's one cycle. In that cycle, we read and write to entry 6. Okay? So does it work? Yes, except the problem is we're writing dead beef, but the value we get out during that cycle is 6. That's the old contents, right? Well, that doesn't work for the processor. Because if you have an instruction that writes a register, right, and you have a pipeline CPU, so the instruction that writes the register is in the write back stage, and you have another instruction that comes after that instruction that's reading that same register, right, you expect it to get the updated version, right? So this is something they call a register bypass. It basically says that you put a special case in there that says, if you happen to be reading and writing the same register, if your read address 1 is equal to the write address and you're writing, write enable is asserted. So if you are writing and you're also trying to read that same entry, then spit out the write data as the read result. Make sense? So basically it says, this creates a multiplexer that basically says, don't wait for it to be written. If you're reading and writing the same value, then put the new value out. Don't put the old value out. Bypass the old value. Take the new value and send it directly to the output. Don't wait for it to be written to the RAM. That's what that does. Now this is only for pipeline CPUs. This is something too they should have covered in 2.12 because this is part of the Mips CPU too. They probably didn't emphasize it much though because you weren't actually building it, right? They might have just mentioned it in passing. Okay, and then finally, if neither one of those cases is true, then you just say mem of read address 1. That's the read. Does that make sense? So then that code is copied and pasted basically twice, except read address 1 and read data 1 are made into read address 2 and read data 2. So that's kind of just copied. And then down here we have the write port, which is just one always statement that says the write. If write enable, then write to the right address in the memory. So that's the register file for the RISC processor. And all you have to do is basically connect stuff to it to use it. Yes?
So you mean to say that if you read, whenever you say you read and write to the same register, you mean what exactly? You mean like an add instruction that?
Yeah, so when you write, there's basically a cycle. Writes are synchronous, so there's a whole cycle of delay. So basically, when you write, you have to wait a whole cycle. You have to sit there with write enable asserted, and the address asserted, and the data you want to set in there asserted for a whole cycle, right? And nothing actually happens until the end of that cycle on the rising edge of the clock, right? The problem is that any reads that happen inside of that cycle, especially, you know, asynchronous, well, I shouldn't say especially, only asynchronous reads, because asynchronous reads would take a cycle. So inside that cycle where you're trying to write, if you try to read, right, normally you would get the, you know, you just get the value in the RAM, which is whatever was in there.
That's sitting there right now, that isn't.
Except what's being written now, yeah.
The new value hasn't been written yet.
Right, the new value won't be written. So that's shown in this thing right here. When in this cycle, now again, there's one cycle I'm writing. I'm writing to register 6 in this one cycle from rising edge to rising edge. I'm writing to register 6, but the value I'm getting out is not dead beef. I'm trying to write dead beef in there. I don't get dead beef out. I get 6 because that's the previous contents of that register, right? So if I had the bypass path, which is the code I showed you, then that dead beef would have showed up there, right? Because I would have bypassed, right? So even though dead beef hasn't gone into the register file yet, it still would have been indicated as if it was in there. It's like cheating. It's like, I know I didn't get done with the write yet, but since it's coming in right now, I'll just send it back out, right?
But is there a way that can happen architecturally? Like,
yeah, it's literally just a multiplexer where you have a multiplexer that says.
Like, I know the solution is fine, but like, is there a way that we can architecturally run into that problem?
Yes, yeah. If you have in your pipeline CPU, so we're building a 3-stage pipeline, and so it's simplified. It's not a 5-stage, but even in a 3-stage pipeline, if you have a register that writes, if you have an instruction that writes register 5, and the very next instruction reads register 5, then you'll have in one cycle, you'll have the first instruction will be writing back, meaning writing register 5 in the register file. The next instruction will be in the decode stage, reading register 5, right? Now you might say, how often does that happen? All the time.
Yeah.
It's very common to do that because when you take a line of C code and you break it into assembly, the C code is more abstract, so you're always calculating intermediate results that you use in the next cycle, always. Almost every instruction is like that when you're doing arithmetic, at least, right? You're always writing a register and then reading it in the next stage, right? You write a temporary and then you use it to build up the expression, right? So it's very common to have that, but in a pipeline CPU, that results in a read and a write simultaneously because the read ports are on the previous instruction and the write port is being used on the current, the write is being on the write port's being used on the first instruction, and the read ports are on the next instruction, sorry.
The execute stage is using the write.
Right.
The decode is using the read.
Yes. Yes.
And even if we have asynchronous, that's still a problem.
Yes, yeah, the asynchronous doesn't help you. The asynchronous read doesn't help you because the write is synchronous. You got to wait for the write to happen.
Because
right.
execute is here and decode is here.
Right. Read, if you have an asynchronous read, the read happens instantly, but doesn't help you because you still have to, it happens instantly once the data is in the RAM, but the data takes a cycle to put in the RAM.
Okay.
Okay, so that's what's happening there. But again, we're going to give you that code, but you do have to, as long as you understand we used to have this as a project in this class, actually building this and designing a test bench, but it was boring, and it wasn't that much work to do for a whole lab, so we decided to just give it to you, that way we can get into the CPU faster. Okay, another thing we're going to give you, I'm going to switch gears here a bit. Another circuit we're going to give you, another module that we're going to give you as part of an IP library block, is the ALU. So the ALU is simpler than the register file because it's combinational only. It has an A input and a B input that are 32 bits, and then an op input which is 4 bits that just specifies what you want it to do. And then a R output, which is the result, and a 0 output, which is confusing because a 0 output is a single bit control signal that's true if the result is 0. You might say, why in the world would you need something like that? For branch instructions. Like because when you do a branch if equal, you subtract 2 values, and if they're equal, the result is 0, and therefore you use that 0 as the branch resolution. Okay? Okay, so that's the top level interface for the ALU. That's the module line there. This over here on the right, if you look at the right, this is a table of the ops, ALU ops, and the resulting function. Now the problem is that there's actually only, I think there's only 13 unique operations, but yet, because it's a 4-bit opcode, there's 16 codes, right? So some of these are redundant, like for example, these two. 1010 and 1011 are both right arithmetic shift, right? And you might say, is there any better way to handle that? No, I mean, if you only have 13 functions and 16 codes, some of the codes will have to be, redundant. So those are redundant. These three are redundant. An op of 1101 is an A less than B unsigned, as is the other two codes, 1110 and 1111. You guys with me on that? So each of these operations correspond to one R-type instruction in the instruction set. Okay, so what do we have? We have bitwise operations AND, OR, XOR, which correspond to the AND, OR, and XOR instructions, right? Then you've got plus and minus, which is add and subtract. Now you might say, is there an unsigned subtract? No. Not in RISC-V. There is in Mips. RISC-V doesn't care about unsigned subtract. Unsigned and signed subtract are the same thing. The reason why it was different in Mips is because Mips actually had an exception, an overflow exception, but RISC doesn't have an overflow exception. They got rid of that. Then you've got multiply. Now multiply, does multiply care if it's signed or unsigned? No, not if you're only taking the low order 32 bits of the product. If you look at the high order 32 bits of the product, then it matters. So there's a multiply high signed and unsigned, which you guys know about because you used that in Lab 1. You took advantage of that. So there's two versions. Now you might say, wait a second. I thought you said in Verilog there's no unsigned and signed data types. It's just logic. So how does the Verilog know which one is which? I'll show you. That's a weird, something strange you have to do in Verilog to implement that. But yeah, there's two different multiplies, and then there's left shift and right arithmetic shift. And then these are comparisons. A less than B. You might say, wait a second, A less than B is illogical, but you've got 32 bits coming out. Yeah, you pretty much just waste 30, like whenever you do this operation, the result is held in bit 0 of R. And the other bits are just kind of wasted. They're set to 0. They're the same way in Mips too. Other processors, by the way, like ARM, when they would do something like that, they use the status register. You would do a comparison and the result would go in a status register. And then subsequent instructions could check the status bits, right? That's a very common way to do it. RISC doesn't have a status register. Because you might say, why? That makes sense, right? Have a status register that gives you the result of the last arithmetic instruction, right? That way you don't use up one of your general purpose registers. Yes, the problem with the status register, though, is it becomes a data hazard in the hardware. And it complicates implementation. So they don't want to use a status register. They want to use a register to pass these comparison results because it simplifies the pipelining. It simplifies the number of bypasses that you have to forward, basically. If you don't understand what that means, it's not a big deal. It's just an aside. Okay, this is the ALU code. Again, we're going to give this to you. It might look complicated, but it's actually pretty straightforward when you look at it. So we do some things in here, like for example, for the multiplies, you'll notice that we have we use this thing where you can, on the left hand of an assign, you can do a concatenation. I think that's cool. I like how you can do that. You can also see that we use $signed to tell Verilog to do a signed multiply. Okay, that's the one exception where you can actually tell, well, the one exception that I've encountered where you actually can tell Verilog if it's a signed or an unsigned data type. So this is a typecast, basically. It's the only time I ever use, well, I think I used that with a comparison once, but yeah, it usually only comes up with these ALU type things. Okay, now the shifting. This whole block is the shifter. This is the barrel shifter. Barrel shifter means that you can shift by an arbitrary number of bits in one cycle, as opposed to having to, bit for bit, one bit at a time in each cycle. That would be a shift register. This is a barrel shifter. Now you might say, well, wait a minute, I thought you said that Verilog has a shift operator. Why didn't you just use the shift? Why did you do this crazy thing where you did this crazy logarithmic shifter? We never could figure that out. We tried to use the Verilog shift. We couldn't make it work in here, so we ended up building it kind of at a lower level of abstraction, where basically we did shifts, but not using the Verilog shift operator. We used the concatenator and basically shifted, kind of like I showed you in my little demo with a linear feedback shift register. But when you do it that way, you have to shift by 1-bit, 2-bit, 4-bit, 8-bit, and 16-bit, and then through a combination of those, you can shift by 0 to 31 bits using the blocking assignment statement. So that's a very quick summary of how this works. You don't really have to understand how that works, but that's shifting. And then this is just a big mux. Actually, sorry, I take that back. We did use shifting here for the logical shift. It was the arithmetic shift that we couldn't get working. What we tried to do, I remember now, I forgot about that. We tried to do shift combined with this signed typecast to do an arithmetic shift, and that was what didn't work. So we did the arithmetic shift with that. But we're still doing logical shifts with the regular shift operation here. Okay, but anyway, and that's and then we used also sign for this. Yeah, this is, as I mentioned, this is the signed comparison. Okay, makes sense? The multiply, by the way, the multiply takes advantage of intermediate values that we declared here and set here. So I don't know if this is the most efficient way to build this ALU. Probably isn't, but this is the one we've been using for the last, we've used different versions of it in the past, but this is the one that we've been using for the last 3 years. Any questions? Yes?
How do you do branch less than?
Well, that's part of the control unit. In order to do branch less than, you mean with this? Well, branch less than is you basically, you set the ALU to do less than, and then use the result from the ALU to then have the control unit take the branch, meaning that you update the program counter with the appropriate branch target address.
So you have to use the ALU and not put it anywhere.
Yeah, exactly. Yes, that's a good point. Yes, that's a good point. So what he's saying is, when you do the branch less than, you instruct the ALU to do this, but you don't actually save the result of the ALU in the register file. You only use it as a feedback thing to the control unit to then take the branch, to resolve the branch. So yeah, it's a good point, yeah. You don't necessarily always save the results of this ALU stuff into the register file. Sometimes you just use it as control. Okay, so we're going to give you the register file and we're going to give you the ALU. You guys will be responsible then to use those to build a RISC CPU that implements 22 instructions in Lab 3. By the way, the lab sheet is already posted. It's due on October 30th. So you have 4 weeks to do it, which in the past has been more than enough time. And then the TAs will go over the lab sheet in lab. But I just want to introduce it. So there's 22 instructions in the initial list that we want you to build. And again, the way you build this is you start out by creating a CPU module, and then you're going to plop in your ALU and plop in your register file. And then the biggest component you will have to design is the control unit, which I will show you how to build that in a minute here. And then you wire everything together, and that's essentially the CPU. In a nutshell. But there's 22 instructions. Most of them are just number crunching instructions like add, subtract, multiply, and, or, shift. There are a couple weird ones though. This one is load upper immediate. The load upper immediate takes an immediate value and sticks it in a register, but it sticks it in the upper bits of a register. The upper. And what's even weirder is Mips did load upper immediate with 16 bits. But RISC-V has a 20-bit. It puts the load upper immediate takes 20 bits and puts it in the upper 20 bits of a register. And then I/O, you might say, why 20 bits? Well, because they reduced all the other immediates to 12, and they had to have a complement to the 12. 12 and 20 is 32, right? And then there's this R-type I/O, which is CSRRW. You might wonder, why are we adding a complicated I/O instruction? Because this is the way that your CPU will interact with the outside world. Specifically, it's the way that you'll read the switch values coming into the CPU, into a register, and it's the way that you'll take a register value and kick it out to the 7-segment displays, right? That's what this instruction will be used for. And that's a real instruction. I mean, that's a real instruction in RISC-V. Okay, so let me talk. I only have a minute here. I just want to briefly introduce this. So one of the differences, when we switch from Mips to RISC-V, the biggest difference, they're very similar, but the one difference that you get clobbered on is the instruction encoding formats. They are radically different than Mips. Everything you learned about the Mips encoding formats is all gone. So this is all different. So remember, Mips had just 3, R-type, I-type, and J-type, at least in integer instructions anyway. Floating point had other formats. RISC-V has a lot more. In this lab, we're going to deal with the R-type, the I-type, and the U-type encoding format. And they're all kind of weird. The opcode doesn't come first. There's a weird function in the field in the middle of the instruction. The opcode is 7 bits when you guys use the 6-bit with the Mips. So all that stuff is, and there's no shift field anymore, shift amount field. Remember you said shift amount, right, in Mips? That's gone. So this stuff is all different from what you learned in 212. But it's not a big deal, because as long as you have this handy, then you can figure out what the bit ranges are, the bit fields are. You just have to refer to the little map. Okay, that sounds great. Then we'll see you next week.